Okay, one of the tasks that I need you guys to be able to work on is being able to start using some of the formulas, some of the math that we're going to do in physics. Because from here on out, pretty much everything is going to involve, every day we're going to learn a new formula or two. This is just a review of the one formula we've done so far. V is d over t. And V can stand for either velocity or speed. So if it's a speed, we don't care about direction. If it is a velocity, we throw the little arrow hats on top, just to kind of let us know that we care about which way we're going. This first example is pretty straightforward. All you got to do is take 8.25 feet and divide by 4.50 seconds, and you've got an answer. Like, it literally was just divide two numbers. But the more important part here is I need you guys to get the other little details down. Okay. Right now, it's pretty straightforward, I hope. So what did you say you got, Gustavo? Okay, so I had a couple of questions from kids. It's actually 1.83 repeating. If you were to write this, I would want to come back at you and say we can improve our answer, I guess. Okay, I wouldn't say this is necessarily wrong, but like the details are important. Okay, I know it doesn't seem like it now, but let me give you a real world example. Actually, I don't remember the year, but sometime in, like, I believe it was the 90s, NASA, the space agency, they sent a rover towards Saturn or Jupiter. And they spent billions on the project, and they wanted to land a rover on the surface of Saturn or Jupiter. I forget which one it was. They subcontracted, they divided the work up between different people. And some of them were using units like feet, and others were using units like meters. Have you heard of this one? And what ended up happening is they didn't round some numbers properly. And you might think, who cares about rounding, Chris? Well, this is actually a classic story that gets used, is that when they converted between feet and meters or something like that, they rounded slightly. And they missed Saturn entirely. Now you might think, well, like they missed by like the smallest rounding amount, right? But imagine that you're flying a spaceship between here and Saturn, and you're off by like 0.0001%. If I'm off by like that amount, like here on Earth, I probably don't notice the difference. But when you're traveling hundreds of billions of miles, if you're off by the slightest fraction, it's going to miss entirely. Right? I don't know that I can kind of illustrate this, but like, we can draw a diagram. If here's Earth and here's the planet you're going for, and you were supposed to go here, and like you were off by just the littlest fraction, right? I'm just slightly out. Well, right here it's not a big deal, but then like over time, because it's so far away, can you see how it would start to become an issue, right? And so like this small little percentage caused them to like screw up like $1 billion rover of some type. Right? So now, granted, I know you guys probably don't all have aspirations to go be NASA physicists. But I want to really reinforce these concepts now while the equations are easier, because the math is going to be more challenging than just divide two numbers. So here's the points I want to make. First thing is we need to round it. We can't just leave it as 18.3 repeating. We have to know how much precision we're allowed to keep. Okay? This has 3 digits. This has 3 digits. So my final answer better have 3 digits. Okay? So that's step 1. Step 2, I need to have proper units. The units for this would be feet per second. And that's really important because a foot per second is different than a meter per second, which is different than a centimeter per second. We got to make sure we have the right units nearby. In general, in my physics class, if I ever see a number written down, I should probably expect to see a unit afterwards. I don't usually want to see 3 divided by 2. I'd rather see 3 meters divided by 2 seconds. And then last thought, we should consider whether we need a direction or not. And since it wanted speed, I don't really care which way we're going. So 1.83 feet per second is what I would grade as like being correct. Fair enough? Okay. Let's try another one. Do you guys hear a little squeaking kind of sound like someone's moving furniture? Yeah. Is that me? Or that's you hear that too? Okay. Okay, let's try another one here. The second question, in terms of the variables we have, I'm going to utilize the formula here. It says that we have a speed of 34 meters per second towards home plate. So in a way, now the velocity is 34 meters per second. and it says that it took 3.8 seconds, so that means the 3.8 seconds is down here. What we don't know is our displacement. Now, there's a couple different ways of solving this. If you understand your algebra, all you have to do is just times this number up to the other side, and that's it. But I want to show you guys like another tool, I guess, if that makes sense, on a new slide here. Some of you have already seen this before. It's where you make a triangle out of things. And the way this would work then is that your formula was that V equaled D over T. And so if you've never seen one of these little triangle manipulatives, what you have to basically do is just cover up whatever it is you are looking for. So on this example here, since we are looking for our displacement, what you do is you just cover up the distance here. And then based on these two things being in the same row as each other, then you have to multiply them. So if you were to take your velocity of 34 meters per second, and you were to multiply by your time, which was 3.8 seconds. Okay, a couple of thoughts. There's totally desks being moved around, isn't there? Oh, that's annoying. Okay, can you guys see how this second and this second right here, can you visualize how those cancel? Because like one's in a denominator and one's in a numerator, they cancel. What are you left with for units? Meters. Well, isn't meters what we measure a displacement in? So all I have to do is the math now. 34 times by 3.8, and I get this number here, 129.2. Still not correct. I mean, it's not necessarily wrong, but we need to be more exact than this. Okay? It has to do with precision. This digit right here had 2 digits of precision. This had 2 digits of precision. And this now has 4. We have too much. So we have to round this back to 2 digits. So the number 129.2 is only allowed to have 2 digits when I'm done. Now this causes us a problem. I can hack off this digit right here without any problem. But let's say I try to remove this digit right here. Well, I can't all of a sudden make something that was 130 at 12. Right? Now, sometimes what we can try to do is try to round this. I could say that this rounds to like say 130, but like even then that's still a little ambiguous. Was that rounded to the nearest 10 or the nearest ones? So the best way of doing this is to write it like this. 1.3 times 10 to the 2. I'm going to move the decimal place over 2 times. Keep the 1 and the 3 that it rounds up to, because it kind of does round up to the nearest like tens now. And then my unit is meters. Last thought, this one actually wanted a displacement though. Sometimes we care about direction. If the baseball player threw it this distance, can he throw it any way he wants? Well, no, because if he throws it to right field, then the runner steals home, right? So like we need a direction, and sometimes it's just as simple as like towards home plate. Like something like that. I don't know what exactly you're going to write, but you're going to want to have some sort of direction, because sometimes it matters which way you throw it. Right? So he's got to throw it towards home plate. He can't throw it into the outfield. Okay. There are some things, though, where we just don't care which direction you're traveling. Make sense? Cool, one more. Same formula, V equals D over T. I'll bring up that same little triangle thing here. So if you like the triangle concept, it's V equals D over T. But on this example here, I'm now going to give you the speed of sound. That's a velocity. And I'm going to give you a distance. What we're looking for is time. So if we're looking for time, what we have to do is we have to divide the distance by the velocity. So really the formula is time is distance over, let's see, it goes like this, distance over velocity, like that. Now, if you want to talk about the algebra behind it, here's how that worked. The formula was V equals delta D over delta T. What you're really doing is flipping these two, flipping their locations. If you ever heard of the phrase cross multiply and divide, that's what's happening here. You're cross multiplying up time, so that time is over here, and then you're dividing out velocity, so velocity comes here. If the algebra part of this is a struggle for you, we need to talk, okay? Because there's kind of a little bit of an assumption that you guys have covered like algebra previously in grade 9 and grade 8, but I can help with that if that helps. So long story short is we need to throw in some numbers. Your distance was 2.5 kilometers. And your velocity, sound, is 340.29. So 340.29 meters per second. If you divide these two numbers here, we're going to have a problem. Why should I not divide these two numbers just the way they are? Anyone know? Nicely done, yeah. One is in kilometers and one is in meters. And so that really doesn't like jive all that well. So I threw this example on to remind us how to work with a kilometer. Kilometer is 1,000 times more. It's 10 to the 3. So maybe it's better to write it like this. We actually have that many meters divided by this many meters per second. Now this works better. This is a times 10 to the 3. Now watch this. Your meters symbol will cancel. What unit's left? Seconds. Isn't that the unit for time? Perfect. Okay, so let's do 2,500 divided by 340.29. And I'll go over this way here. So this is our time. For time, I got this. 7.3466, etc. But again, I need to round. So what had the least number of digits? Yeah, this 2.5 right here gave me 2 digits. And let's talk about this number for a bit here. This 2.5 kilometers, if I could have measured it better, maybe it was actually 2,499. Maybe it was that. And we rounded it to 2.5 kilometers. But maybe it was like 2,451. Maybe it rounded that way to get to 2.5 kilometers. So like, I don't really know exactly how precise this number is. And so since I don't know with much precision this number here, I have the same problem here. I need to like cut it off right there. It would be 7.3 seconds. Okay. Can you do this? Okay. And maybe you can't do it yet. That's fine. Same analogy as I gave a little while ago. Maybe it's like a house that's in the middle of demos. Right? Like we're not there yet. The studs are exposed. There's drywall all over the place. We haven't actually, put on the grout and the paint and the carpet yet, but like we'll get there. Okay. That's what I need you guys to ask for my help for the next little while. Okay. But if you could do this, we're off to a great start. Today, I need to introduce new formulas to you. Okay. And pretty much every day that we do a new lesson, I'm just going to show you new formulas, and we just add them to our list. Okay. So today's concept now is about acceleration. Okay. All those previous formulas were about something called uniform motion. Okay. Acceleration, we would call it non-uniform motion. Let's just talk about those words there. If we had uniform motion, that kind of means that you're like going the same speed the whole time. Right? Like if you're just going a nice constant speed, you're on cruise control, you're not accelerating. You're just... Non-uniform motion means one of two things. You are either speeding up or you're slowing down. Does that make sense? Right? Like there's 3 possibilities. Either you're getting faster, you're going the same speed, or you're going slower. Okay. Yeah, I think that kind of stands for itself here. Here's what I need you guys to know then. If you ever have a positive acceleration, it means you're going faster. If you ever have a negative acceleration, it means you're going slower. Okay. Imagine a car, right? Say I need to get my car into the highway. I press on the gas. What am I doing? I'm accelerating. Then I'm on the highway, right? I set my cruise control and I take my foot off the gas. Now I'm going at uniform motion, same speed the whole time. All of a sudden I see an accident ahead of me and I decide, I better slow down. I hit the brake. The brake is a decelerator. Like you guys probably know these words. So here's our new formula. A equals V over T. We can actually use the exact same triangle concept, if you like, to try to help solve these formulas. An acceleration is a velocity over a time. I really messed that up. Let's fix that. We don't put a line up here. There we go. This is better. So if you ever want to figure out how much acceleration you have, find your change in velocity over your change in time. Hopefully you guys recall that this little triangle is the Greek symbol delta, which means the change. In order for this to work, you actually have to change your speed. You have to have been going 5, and now you're going 6. or you were going 20 and now you're going 3. Something has to change. If your initial speed was 10 and your final speed was 10, nothing changed, right? So let's try some examples. Yeah, here we go. Here's an example. So let's say there's an object that starts at rest, and it accelerates for a time of 12 seconds. But I'm going to be very specific. I'm going to care about the 5 to 8.7 second interval. Okay, so like, here's time. This is like a timeline. It started here, and then it accelerated from 0 to 12. But I only care about the 5 second interval to the 8.7 second interval. During this time frame, I want to figure out what sort of acceleration, that's an A by the way, what sort of acceleration the car had during that time frame. And so I gave some numbers. I said that it accelerated from 15 to 27.8 meters per second. Let's find its acceleration. Okay, so our new formula. I'll throw it down here, hopefully there's enough room here. Our acceleration is the change in velocity over the change in time. How does this delta thing work again, though? It's the change, right? One of the ways that we can work with this delta thing is we can find the final and the initial numbers and kind of subtract them, right? Like, for example, like, it was going 15, now it's going 27.8. How much faster did it end up going? Well, what we really need is 27.8 minus 15 meters per second. I got to figure out how much difference there was between those two numbers, which is 12.8, yeah, right? I went 12.8 faster. And then I need to know how much time elapsed. Now, I mean, there's 3 numbers for time. There's 12, there's 5, and there's 8.7. None of those are what I'm going to use by themselves. How long did it take to go from 5 to 8.7? I think it's 3.7. But like, what did you really need to do? You had to take 8.7 and subtract 5.0 seconds. And I'm going to need to like go to a new slide here because I'm clearly running out of room. So let me rewrite this on a new slide here. A was equal to your change in velocity over your change in time. And I'd previously written 12.8, no, 27.8 minus 15. That was in meters per second. And my time was 8.7 minus 5. So I can do this like in multiple steps now. 27.8 minus 15 means that I changed my speed by 12.8 meters per second. And 8.7 minus 5.0 means my time took 3.7 seconds. Is that kind of clear how I like found those two values? And then now I divide them. So 12.8 divided by 3.7. How fast am I accelerating? I got this. 3.459, 459, 459, and like that goes for forever. Typical physics conundrum, how do we round? Find your lowest numbers of significant figures. When we measured these numbers here, this number here had 3 units of precision to it. But this one had 2, this one had 2, and this one had 2. It's kind of arbitrary, but like to be consistent, the rules we've gone with are just go with the lowest number. So 2. So round this number to 2 digits. So keep the 3. This 4 right here would round up to a 5. And here's the units we use. It is meters per second, and we square the seconds. That's how we write it. And that is the unit for acceleration. You're right. And so this seconds right here, how do I explain this nicely? It's like it's meters per second, and then you're dividing by an extra second. Okay. Maybe that's like meters per second divided by seconds over 1, if you can agree with that. When you do a fraction, divide by a fraction. I don't know whether you've ever heard of the rule called multiply by a reciprocal. But what ends up happening is this meters per second stays that way, and you multiply by the reciprocal of this thing here, where you flip that upside down. And what ends up happening is you have meters times 1 on the top, and seconds times seconds on the bottom, which is where the squared comes in. So maybe what you were thinking is that these seconds right here, they cancel. They don't. They actually like combine with each other. Does that make sense? Okay. I can give you more of a math lesson on that later if you'd like. But. Okay, we actually do miss one thing though. Acceleration is a vector. We need to know whether or not it's forwards or backwards. I mean, it's a little thing here, but like this acceleration, were we speeding up or slowing down? We were speeding up. So maybe like the letter F would be useful, just to indicate that we're going forward. Because what if we were slowing down? You can still be traveling forward, but your acceleration can be pulling you backwards. Classic example, anyone ever seen like a drag racing speed car that when it gets up to full speed to slow it down, it puts a parachute behind it? Anyone ever heard or seen one of those? Right? It's still going forward, but isn't the parachute trying to like pull it backwards? Right? And so whenever you're braking, your acceleration would be going like negative. So we could even, if we wanted to, rather than doing forward, another possibility would be to do like a positive. And the positive kind of implies that like we're speeding up. But if you were to ever have a negative number here, if we had a negative number, that would imply that like you're braking. So, but I'll leave it as positive because we're speeding up. That makes sense? I hope I don't ever come across as like making light of anyone who has struggles, but what I need you guys to know about physics is that the math is actually fairly straightforward. You are either multiplying or dividing numbers. Once in a while you add and subtract. We're not talking about huge complicated stuff, but you just have to make sure you do it in the right order. You have to make sure you subtract the right numbers and divide the right numbers, or once in a while you multiply. Practice will help, obviously, right? The more you do it, the more you'll be like, oh, I know what to do in this scenario. So let's try another example here. Let's say that I tell you that the boat has the ability to accelerate at 4.5 meters per second. And why don't I make it a little bit more clear? I'm going to make that a positive number. And the reason why I've made it a positive number is that like it said accelerate. If it said decelerate, I would have went with like a negative number. So I'm going to tell you its change in speed is 18.5 meters per second. We want to figure out how long this will take. So let me show you two different ways of solving it. They're really the same way. Here's the first one. I'm going to write out the formula. Your acceleration is equal to your change in velocity over your change in time. And if you like to do this, you can just plug in some numbers. 4.5 meters per second squared is your acceleration. Your velocity was 18.5 meters per second, and we don't know your change in time. Yeah. Say that again. Yeah. Oh, good call. Yeah. So, okay. So it just implies, you know how this was a positive right here? Even though it said speed right here, I think we can assume that it was going forward, if that makes sense. So sometimes I might use the word speed, and we can kind of imply that, like, I know it just gave me the number, but I'm going to assume we're going forward. So can I change that then and just say velocity? And then I'll just put like an F for forward afterwards. Does that work the same way? Good question, though. Great question. Okay, now if you like doing it this method here, you just need to know what the algebra is. You need to cross multiply and divide these two terms. So if you want to solve for your time, the algebra is you rearrange these two, and you divide them in this order. Here's what ends up happening. This meters cancels this meters. This seconds cancels like one of the 2 seconds there, and you're left with seconds left. So the math is really 18.5 divided by 4.5, which is 4.1 repeating. But I don't want to see 4.1 repeating. I want to see 4.1, and the unit is time, so seconds. There, that's how long it'll take. And if that makes sense to you, that's awesome. But let's say that doesn't make sense to you. Maybe the triangle method works better. I'm okay with that. I don't initially show kids the triangle method because I know that it fails at a certain point. There are some questions you can't use the triangle for, but this one you can. So here's your formula, A equals V over T. If you're looking for time, cross out time. What's the formula now? V divided by A. Well, isn't that what I ended up with right here? isn't this my v divided by my a? So like really, this just kind of goes to there anyways. So again, I don't want to make light of making this seem like, oh, this should be really easy for you, because I get it if it's challenging at first. But like, what I do need you guys to know is that you're either multiplying or dividing numbers. That's it. You got to figure out which order to do it in. Make sense? Let's try one more. A car applies its brakes and it changes its speed from 16.5 meters to 12.2 meters in the course of 5.2 seconds. What's the acceleration of the car? Why don't you guys try this one? I've done a couple by myself. Let's try to take this to the next stage. Let's have you try it without me doing it first. So take like a minute or two, see if you can figure it out. I'll give you a hint. This is a bit of a trick question because the details are going to be really important when you're done. The math is pretty easy, but you may end up getting it wrong if you're not careful on the details when you're finished. Good. You kind of caught what I'm going for here. Because although I use the word acceleration here, Braden's realized that you're braking. You're slowing down. That changes something for us. If you have this as your final answer, that's what we want. The real important thing I wanted to point out on this one right here is the negative sign. Now, you don't have to do it exactly the same way I did. I did 12.2 minus 16.5 to get a negative 4.3 meters per second. If you flipped these two numbers around here in your math, and you had a positive 4.3, that's fine. But like at the end of the day, somehow you have to indicate to me that like you're going backwards. The most common way would be to say that it's a negative acceleration, which means it's not actually acceleration at all. It means it's deceleration. You could write it like this, by the way. You could say 0.83 meters per second squared, and then like say b for backwards. That would be fine to kind of imply that it's going like in reverse. Maybe you could even use you could use r for reverse maybe. Right? Something to indicate though that you are slowing down. Because if you don't indicate that you're slowing down, someone might look at that and think you're speeding up. Right? And again, if you're a NASA engineer who's trying to design a space shuttle and you're not careful about that little detail, and you say we need this much thrust, the direction matters, right? Because if you're thrusting to like the left or the right, you could go the completely wrong way, right? Or if you're speeding up versus slowing down, same thing. Anyone have any issues calculating that number? Okay, next thing here then. This is actually going to be in preparation for our lab. I want to do a lab on Monday. And what we're going to do is we're going to race some Hot Wheels cars down the hallway. And we're going to calculate some data. I want to collect data and have a real world scenario where you guys try to calculate some variables. And with where we're at right now in our course, there are now 4 variables we have. There's distance and displacement. So this is like how far you travel. So if you can kind of imagine us racing Hot Wheels, it's pretty easy for us to measure how far they travel, right? We just shoot a Hot Wheel down the hallway, and we take a tape measure, measure it. Right? But here's some things that are a bit more challenging for us to calculate without doing some math, like how fast was the car traveling? How was it accelerating or decelerating? When we shoot the car down the hallway, it's eventually going to slow down. We're actually going to be looking for deceleration. And then the last variable we have is time. Okay? And so there's really these 4 variables. And there are some formulas that merge more of them together. So far, we've learned 2. Acceleration is your change in velocity over your change in time, and your velocity is your change in displacement over your change in time. These formulas right here both nicely fit the nice little triangle method. One of the reasons why I don't show that right away, though, is that not every formula in the world can use the triangle method. So, like, it's a good way to start, but I'm now going to show you 2 new formulas that don't involve this method, and so we need to have some algebra skills to work with them. Here are the formulas. Okay? And I will give you these on, like, your formula sheet. I don't believe they're written down on the one you currently have, and I think even some of your periodic tables, like on the back side of that periodic table was supposed to be a whole bunch of like formulas, and some of them didn't print nicely. Do you guys have your formula periodic tables nearby somewhere? On the back side of it was like a big list of formulas, and some of them like got garbled somehow. So I will always give you these formulas, by the way. You don't have to memorize them. You don't have the periodic table nearby? Yeah, okay. So if you have it nearby, I'll stand at the front here. I don't know why some of them got so garbled up. But okay, so front page, right? Inside pages we've been working with. If you go to the back page right here, there's some formulas on here. And like, I don't know why, but like none of these here like worked at all. Okay? Feel free to write in every single formula I show you on this back page here. And I don't know why this didn't work. The photocopier sucked. Because yeah, yours is all garbled up too, hey? Who did I steal that from? Was that yours? So we now have 4 formulas. So feel free to write them down on the sheet already. Here's the first 2. I'll go back to the slide. There's the A equals V over T formula, and there's the V equals D over T formula. You can probably see where it was meant to go on that sheet there. So write those down if you like. And then in a second here, I'm going to show you 2 new formulas. Right, so like what I might do for yours here is I would just change this. This should be like your V equals D over T. Okay. And this would have been like A equals V over T. Okay. Right, like that. Somehow it didn't work. I don't know why. Stupid photocopier. Okay, so if you're okay with having those old 2 formulas, here's 2 new ones we're going to work with. And one of the things you're going to notice right off the bat is that this got a lot more complicated. The old formulas I gave you were the nice triangle formulas, which we like at first. Most people are okay at that. But like as we get further into physics, I mean, if you guys take my Physics 20 and 30 courses, like, you know, ask a Physics 30 kid for their formula sheet. There's like 80 formulas on there, and some of them are simple, and some of them are like, oh, wow, there's a lot of variables there. So that's what my goal is, to help kind of build you up there. So let me describe these 2 formulas for you. The first formula here and the second formula are actually very similar to each other, but there's a slight difference. Can you guys see how there's a little I sitting right down there? And right here there's a little F. Anyone have any guess as to what I and F stand for? Initial and final. Yeah. And the reason why is that when you have speeds that change, we need to know whether or not it's your first speed or whether it's your second speed. And why do I know that speeds are changing? Because we have acceleration. Right? When you have something that's accelerating, the speed is changing. And so these are a little bit more complicated to work with. They involve multiple variables. And so my goal today and over the next 3 weeks of doing physics is to help you guys be able to work with these, newer and more challenging formulas. Does that make sense? So. Practice is one of the best ways to do this. So once you guys have finished writing down these formulas, I'm just going to hop into an example. And I think that's probably the best way of trying it. I also think that doing our Hot Wheels lab next week, though, will help as well. Because when I give you like a real world scenario where we calculate our own data, for some kids that helps make connections better. One formula is to find your distance. You need an initial velocity and your time, and then add 1/2 of acceleration times squared. And then the other formula is almost the exact same, only rather than velocity initial, it's velocity final, and rather than adding, you are subtracting. Okay, let's try an example. So let's say that I give you a train, and the train has brakes that are capable of decelerating it at 4.5 meters per second squared. The train has 20 seconds to slow down to a speed of 2 meters per second. How much distance will it need? So if you can kind of picture this analogy here, there's a train that's about to go through town. I used to work in Fort Macleod. This worked really well because like the train tracks go right through town, right behind the school. And so if I tell you the train engineer needs to start applying the brakes to slow down to like town speeds, and he's got 20 seconds to do so, like with how much distance out of town, like should he start the braking process 20 meters away, 500 meters away, 4 kilometers away? You get what I'm saying here? I'm asking you how far out of town should you start the braking process? So what we need to do then is figure out which formula to use. One of the strategies you may find useful is to write out what you know. And so here's a new strategy. I'm going to write out what I know. I know 4.5 meters per second squared. What variable is that? What letter is that assigned? Is that a time, a distance, a velocity, or it's an acceleration? So that's A. There's actually one more problem with this, though. That's actually not the number I should use for A. I should use this number. Why negative? Perfect. It's decelerating. Good. Okay. Let's write down our next number, 20 seconds. What variable is 20 seconds? What letter is that going to be represented as? Time, T. Okay. And then it says to slow down to a speed of 2.0 meters per second. That's a velocity, but is it my velocity final or my velocity initial? It's velocity with an F, velocity final. Why? Because we're slowing down to a speed. And what we are looking for is distance. Distance is what we're not sure of. So the reason why I like to write it out like this sometimes is this maybe helps you figure out which formula to use. Because as we learn more and more formulas, there's more and more choice. And sometimes kids don't like that. Because if I tell you there's only one formula, it's easy. But if I give you 70 formulas, like you're going to get in Physics 30, you've got to figure out, well, do I use this one or that one or this one, right? Like it's harder to narrow down. So then go back through our list. Which of these two formulas fits better? And the second one, right? Because we know the velocity final, we know the time, we know the acceleration, and we use time a second time. So like this formula here kind of fits better. So now I know which one to use. So that's a strategy you can utilize. D equals VFT minus 1/2 AT squared. Okay, let's start plugging in some numbers. And like, yeah, the triangle method's not going to work here. But that's okay, because this one's pretty straightforward. My velocity final was 2.0. Sometimes I'm going to stop using my units here. It's okay on a question like this if you just put the numbers in now. I'm going to multiply that by time, which was 20. Then I'm going to subtract 1/2. I'm going to multiply that by my acceleration, which was negative 4.5. And I'm going to times that by my time again, which was 20 squared. Sorry, I'm running out of room there. That will tell me how much distance I require. This is why I would suggest it might be nicer to have like a better calculator, because doing this on your cell phone is doable, but you got to do it in stages. You almost have to like find what this number right here is, because these two things right here is a number, and then all of this right here is a number that you have to like subtract. So you almost have to do it in like stages. 2 times 20 gives you 40. And then you have to subtract 1/2 times 4.5 times 20 squared. And that's negative 4.5. So then you have to subtract negative 900. So the final answer is 940 meters. that's how much distance the train engineer would need to have in order to figure out when to start putting the brakes on. That got a little more challenging all of a sudden. So can I put an open offer out there? If you kind of got lost going from here to here at any point in here, talk to me. I'll try to help, okay? I try to do this with the whole group at once, but like I understand if not all 35 of you, all of a sudden that clicked immediately. Because like this like stage of doing the math inside here and getting those numbers there, if I lost you at some point, I mean maybe ask me right now if you want. Maybe ask me in 10 minutes when I'm done. Okay. Does that work? Okay, let's try another. Oh yeah, go ahead. Oh, you're right. I was sloppy in my own work. Thank you. I do, don't I? Because 940 implies maybe 3 sig digs. You're right. Thank you. So the best answer would actually be 9.4 E2 meters. Thank you so much. Good call. Thank you. Well done. It's good. Actually, I'm glad because it means what I've been saying is sinking in. I got so distracted on the whole making sure you got the math part right, I forgot to finish off the answer. So, cool. Okay, let's try another example. You're a parachuter, and you are parachuting 1.53 kilometers above the ground. The good news is you have a parachute, because if you didn't, you'd just keep falling faster and faster and faster. And it says you are decelerating at a rate of 6.3 meters per second squared, which is good. It means although you are still falling in the air, you are still going to be going down. Your parachute is like trying to pull you back up. Does that make sense? Like here is you, and you are going down, and you have a parachute, and your parachute is like trying to like prevent you from speeding up more. Right? I guess what I'm trying to get at here is this number right here. When we use this number, make sure we use a negative, because although we are still going down, it's slowing us down. We have a time value. Our goal is to figure out the man's velocity when he initially opened his parachute. So let's do the same process again here. Let's write down some numbers. I was given a value of 1.53 kilometers. Right off the bat, as soon as I say kilometers, I don't overly love that. I'd rather make it this number, 1530 meters. Remember how a kilo is a times 10 to the 3? Let's do that. What letter symbol do we use for like a distance? D. Next, we had 25.7 seconds. Sorry, that kind of got, oh no, actually let's do 6.3 meters per second. By the way, this is another way of writing meters per second squared. Meters per second squared can also be written as meters slash second slash second. They're both equivalent. So a negative 6.3 meters per second squared, that would be an acceleration. 25.7 seconds, that would be a time. And we are looking for what we do not know is a velocity initial. So basically I'm saying this guy right here, he's free falling down to Earth, and his parachute's going to start slowing him down. My question is, how fast was he going when he actually cracked the parachute the first time? Because he was probably going pretty fast, and he needed to slow him down a little bit. So, which formula do we need? Hopefully it's clear this time around we're using this formula. So, on a new slide, I'm going to write that out here. The new formula is D equals VIT plus 1/2 AT squared. I have a little bit of an issue though. Last time around I was solving for D right here. This time around though, I'm solving for VI, which means that like I can't use the triangle method. It means that you have to have some pretty good algebra skills. So I'll try to go slow on this one and explain it step by step, but I mean this very much so. This is a major part where I lose kids. Okay, so if I lose you on this last question here, because this is my last one, right? Find me at Flex, find me after class, and let's talk through the math part of this. So let's start throwing in some numbers. The distance I traveled, that was what, 1530? So I can make this number now be 1530. So that's this number right here going there. I don't know what my velocity initial was. So I'm going to leave that as like VI. I'm going to leave that sitting there. And that number needs to get multiplied by time. And the time value was 25.7. Then I'm going to add 1/2 times A. A was negative 6.3. So that's this number right there. And then I need the time squared, which is 25.7 squared. As of this point here, I'm your math teacher again. How do we like algebra this to solve for VI? That's the verb I use. Okay. So if you're struggling with algebra skills, please ask me for more help, okay? So let me try to describe this to you. What we really have are 3 terms. This is a term right here. This is a term right here. And all of this is a term. And the reason why is that these 2 things were separated by an equal sign, and these 2 things were separated by the plus sign. So I'm going to do this in stages. The first stage I'm going to work with is over here. I'm going to work with this stuff over here. I'm going to find what this number is here. Like, what is 1/2 times negative 6.3 times 27 squared? Like, find that number. What is 1/2 times negative 6.3 times 25.7 squared? Over here, all of this mess over here, I got this number. Negative 2080.5435. You see why I don't think your cell phone calculator is probably as ideal. If you have one of these guys, use it or get one. You need it for math anyways. Is everybody able to get that number that I got right there? The 2080 number? So 1/2 times negative 6.3 times 25.7 squared. Okay, again, if you're having troubles, we'll talk later. I want to focus on these numbers over here then. You still have the number 1530, and you still have VI times 25.7. The next question is, in algebra, how do you get this VI by itself? And the answer to the next part here is, I need to now add 2080.5435 to both sides. 2080.5435. Because if I add it to both sides, it kind of like eliminates it over here. So the next step is I'm going to take my 1530 and add to the number that I have there. So I'm going to add to that 2080.5435. I'm going to add 1530. And so the new number that I have over here is now 3610.5435. And what it's left being equal to is the VI times by 25.7. So, recap. All of the numbers that were right here, I put them all together and got negative 2080. But then there's a minus sign between them because it ended up being a negative number. I added it to the other side over here so that this was now added to this side over here algebraically. The last issue I have, though, is I want VI isolated, and it is being times by 25.7. So to get rid of the 25.7, divide both sides by 25.7. And if I divide both sides by 25.7, now I've solved for my VI. So, long story short, if you do all this properly, I'll put the answer in this top corner because I'm running out of room here. I got this. I got 140 point, like, random stuff afterwards. Something like that. Last question then. How do I round it? Let's go back. Sig digs, I get 2. This gives me 3. This gives me 3. This gives me 2. So let's write this number as 1.4 times 10 to the 2 meters per second. There's a big leap there, hey? Like where we started class to where we finished class is all of a sudden there's a different step. Okay? I will help anybody that needs help on the math part, okay? Because that's probably going to be the single biggest thing that inhibits you from going forward. For the rest of the unit, I just teach you new formulas. And so like I'll show you, here's a new formula, here's a new formula, here's a new formula. And if you kind of get how to like do algebra and rearrange them, and I give you practice obviously, then at a certain point, physics becomes very repetitive. And some kids really like it. If you're a very math-based kind of person, you're like, ooh, I like math. If you don't like math, I'm sorry. The next 2 weeks are probably not going to be your favorite 2 weeks of the course. But I'll do what I can to try to help. So, okay. Questions? Not yet. Okay. So let's say this. We've got 20 minutes left. You guys are free to kind of scatter in a second here. Let me give you a couple of passing thoughts, and then you can go if you want. Number one, if you need, stick around for the next 20 minutes. I would love to chat with some of you individually about whatever, whether it's chemistry or physics, whether it's about this topic right here and algebra. I can put together a small group at the whiteboard table, and we can do some practice on algebra skills if you need. Okay. What I think you guys need to work on then is one of the following two things. Okay, hang on, let me keep your attention, okay, guys? I'm not quite done. I know I'm kind of wrapping up, but here's what you need to start looking at then. One, finish up chemistry. Okay, if there's any chem stuff, start finishing it. But I need you to start practicing some physics stuff now. Apparently I have no internet. Why do I have no internet? Lethbridge Wi-Fi, connect. Okay, go to my website. And there's two things that we're going to start to work on. Like I said, we're actually halfway done learning content. We've now covered 1, 2, 3, 4 lessons. We have 4 more to go. Now, we're not halfway done the unit. Okay, like we still need a lot of practice. Like you probably barely started. But we're going to do a couple of labs. I think you should start on your physics assignment though. Okay. Now, you can print it off if you want. If you really need, I can print it for you. If you can though, try to save paper. That's why I make it all digital. So there are some practice questions you can work on. I don't know that you can see this all this well, but like, here's a good one here. A stunt bike rider goes 39 meters west in 3 seconds. Find me his velocity. That's a pretty easy one. We actually did that to start class. But like as you go further down here, I've got some more questions like a dragster starts from rest and reaches a maximum speed in this much time. We want to figure out like how far he traveled and what his acceleration was. Okay? So I got some practice questions in here for you. And if you need more practice than what I have on the assignment, I can find you more. Okay. The other thing we're going to start working on then next week, Monday, is we're going to do a lab. Okay. And so the lab we're going to do is the deceleration of a toy car. Basically the setup is going to be we're going to race Hot Wheels down the big long hallway, and we're going to launch them, but eventually they're going to decelerate and slow down, right? We're going to take some measurements of distance and time and velocity and acceleration, and we're going to practice math that way as well. That makes sense? Okay, I'll shut up now. So you guys can go where you want, or you can ask me questions. I'll kind of tour the classroom. So thanks, everybody. Let's just pause the video here.